All right, well, hello chemists, welcome back. So in this lesson, what I want to do is carry on our conversation about equilibrium. So this one goes out to Sue. Hello, Sue. So Sue emailed me and said, would I mind making a lesson about the equilibrium type questions, the calculations, all the algebra and everything else. And I said, well, of course I would. All right, so here we go with this one. So, so what we're going to do then is I'm going to move my video link somewhere now to actually see what I'm doing then. So we're thinking, okay, equilibrium. We said last time in the previous lesson that equilibria is a balance between the left and right-hand side. I wish my phone's turned off. All right, the left and right-hand side, the reactants and the products of a system, and it's dynamic equilibrium, meaning that the forward reaction is taking place at the same time that the reverse reaction is taking place. True. We also said that at equilibria, the concentration is of the reactants and products are constant. And I said, yeah, gotta be careful about this one because constant does not mean that the values are the same for the reactants and the products. It doesn't mean that they're equal to each other. No, quality of language, you're thinking what it means is that they are constant. It's not actually moving, okay? And I think last time, didn't we have the equilibrium? I said it's like a seesaw, you know, so you got the reactants and products and it moves up and down and eventually it comes to a final resting spot. And it could actually favor the product side, it could actually favor the reactant side, right? So this is where we left our discussion of equilibrium. Let's say closed system, open system, and isolated systems. And we said, so at A level, what they do is they just use a closed system. So it's like a bottle of water here, another one of like, you know, Tesco's finest here, bottles of water, or a coffee cup from Costa Coffee, Starbucks, the swizzle stick on it. You're thinking the enthalpy can get in and out of the system, true, but the chemicals, the mass, it can't. All right, you've got loose reactants, you've got loose products. Imagine a round bottom flask with the stopper on it, okay? So we then looked at Le Chatelier's principle and we said, right, Le Chatelier's principle is the equilibrium position, as in the side is going to move, is going to favor, is the equilibrium position is going to move to that side to reduce the stress or the disturbance applied to the system, right then. So we then looked at what happens if you add or take away reactants or products, say concentration, increase or decrease the pressure, or especially we spent some time on looking at increasing or decreasing the temperature. Because they said this is the one where it's going to be on the exam. If I was going to write the exam, it would be the one with the temperature, because they're playing around with your understanding of exothermic and endothermic. When I say if it's exo, you put the enthalpy on the right-hand side, and if it's endo, you put on the left-hand side. And then you use the working example of Le Chatelier's principle, which is away from the side you add and towards the side you take away from. So this is where we left it at the previous lesson. And so now on this one, so this one goes out to Sue. Like I said, Sue emailed me and said, would I mind making a lesson about all the algebra and the calculations of equilibrium? And I said, well, of course I would, not a problem. So anyway, here we are. This again, all right, starting out with the Haybird process. Chemists, you've got to understand that there are certain systems you just need to know. Like they'll always ask you the same questions on the same system, all right? And the Haybird process is one of them. All right, so having said that, you know, look at your spec for your exam board and make sure that you've got all the systems down that they can possibly ask you questions on. This is a classic one. So anyway, nitrogen and hydrogen in dynamic equilibrium right here. This is what this means right here. Oops, hold on, put that right there. This is what this means right here is dynamic equilibrium. This is a symbol we used last time to give you ammonia, right? Now, How I think about it is this is the one we're looking at. Think about it like a pendulum, because in year 13 chemistry, we do Gibbs free energy, the Arrhenius equation, rates of reactions, and this kind of comes around again, and you have a more deep understanding of it. But what I'm thinking is pendulum like this. And so on this side, you have reactants, and on this side, you have products. And just imagine that. So when you start, right, the pendulum, if you would, is all the way on the left-hand side, all right? True, because at time 0, all right, at time 0, okay, there are, or there aren't, any products. Yes, you haven't done anything yet. So here's my pendulum. All right, imagine it's all the way on the left-hand side. You've got my nitrogen and your hydrogen, and then you let the pendulum swing. It's going to go back and forth until eventually it comes with final resting spot. So first off, all right, you are completely correct if you say that there aren't any moles of product at time 0. True, because you haven't done anything. And then, all right, they then need to give you some information about what's happening at equilibrium. And so the equilibrium moles is the one that we need to be looking at. So you're thinking, right, if I went from 0.1 down to 0.07, so let me get my calculator out here. Let's do this one live for you chemists, okay? All right, always do these live, all right? So calculator, my trusty iPhone here, right? So it is right 0.1, yes, and you ended up with 0.07, and so that is a change of 0.03. So you're thinking, now, if we went from 0.1, all right, you're adding going down, you add in this table going down. All right, you start with 0.1, use the initial number of moles. All right, you may see this on the exam or on your notes as ice tables. All right, and you ended up at 0.07. Well, then this would be 0.03 of a change, right? The negative, right? Well, then on this one, you're thinking, right, if this is, so 1 mole represented a change of 0.03. So therefore, there's a 1 to 3 ratio in your balanced equation between nitrogen and hydrogen. And so therefore you'd have to take 0.03 and times that by 3, all right, which I just did in my calculator there. So you get 0.09. And so this is 0.03 times 3 is 0.09, right, change. And so you add going down, and obviously this is negative. And so you had, 0.1 minus 0.09 like this, and I'm ending up with 0.01 like this, right? 0.01 like this. Right, now, you're thinking, yeah, but just got a question. Why is it negative on the left-hand side? Well, simple, it couldn't be negative on the right-hand side, because if it was, all right, you would end up with negative moles. And so you can't have a negative number of moles. Can't have a negative value, a negative number of moles. It's supposed to be negative number of moles. So you're thinking, right, so if it's negative on one side, it's positive on the other. And obviously on this one, you're thinking, well, yeah, they told it was 0.07. So 0.1 down to 0.07, you knew you had to lose 0.03. Now, let's see, the ratio between N2 and NH3 is 1 to 2. So essentially what I've got to do is I've got to double this, don't I? So this is 0.03. And so this is going to be 0.06, right? So if you like look at this one and say, right, if 1 mole, change was 0.03. So when you started with 0.1, you ended up 0.07. The change is 0.03 in the negative. Then you're thinking, this is for 1 mole of it. Well, the molar ratio means that 1 to 3 means that you're thinking, you've got to triple it. So 0.03 times 0.09. So it's what's the 0.01 minus 0.09 is now 0.01, equilibrium. And then 1 to 2 ratio means you take the 0.03 and you got times it by 2. And you get 0.06, which means that I ended up with 0.06 on this side, right? So this then is, very first thing is that you got to understand that at time 0, imagine the pendulum of the reactant is over on the left-hand side, and then it's going to rock back and forth, because, you know, we said it's got to be when the rate forward equals the rate backwards, it's going to rock back and forth until eventually it reaches its resting spot. All right, and in year 13, we talk about Gibbs free energy. And then you see the equilibrium, right? Now, you notice we've been saying the concentration values are constant, yes. They're not equal to each other. Well, they're not. 0.07 is not equal to 0.01. It's not equal to 0.06. And so they're not equal to each other. They're not the same as each other. They're constant. So what this means is that equilibrium, the concentration of NO2, of N2 right here is 0.07. Right, so it's not going to move up to be 0.08, and go down to 0.06. No, it stopped at 0.07, right? And we'll talk about how to convert this into concentration in just a bit. So anyway, this was this one. Now, the next one, I put the next one in chemist because little bit tricky, because what you don't want to do is fall into the trap. Let me put this up here. You don't want to fall into the trap of thinking that it's always going to be negative on the left and positive on the right. So if you're doing like loads and loads of past paper questions, I know that you are, thinking, yeah, you don't want to become complacent. Oh, so it's negative on the left and positive on the right, because the exam board will probably put one on, all right, the paper where it isn't, like the next one. I picked the next one because it's negative on the left, isn't it? You think you start off with 10 and you end up with 9, obviously you've lost 1, right? Now, and then come on, so this side's going to be positive and this side's going to be positive, and so you go on to this side. This is obviously a 3-to-2 ratio. All right, so I'm thinking, well, it's a 3-to-2, so minus 1 times 3 is 3 over 2 is 1.5. And in my mind, I'm just saying that the change right here, the change, well, if it's -1 for 2 of them, then it's -0.5 for every mole. So, you know, if you're wondering how I'm doing this so quickly, it's because, right. So you're thinking, right, 10 down to 9, the change is -1. -1 represented 2 moles of ammonia. Therefore, the change per mole is -0.5 going down here. So on this side, it's going to be positive. So 3 times 0.5 is 1.5, like so. And this is going to be 1.5 equilibrium moles for hydrogen. And then the change in moles for nitrogen, well, that's just going to be 0.5, isn't it? And so you end up with 10.5 because you add going down. Right, so just to get us warmed up, if you would, this is how you calculate the moles at equilibrium if you know the value of the change. Would you see this one on the exam? Could do, you could, but you're most likely going to see, if my page changes, one of these. Now on this one then, you're thinking, Right, you don't know the value of the change. And so now on this one, you're going to start using a variable. And well, we're not that creative. We're just going to call it X. Okay. So anyway, again, so this is a system that we did last time. It's a favorite of the exam board because hydrogen and iodine give you 2HCl. You've got the same number of moles on either side. And so they'll ask you, well, what happens if you change pressure? Well, nothing happens if you change pressure to the equilibrium position because you've got the same number of moles on either side. But here we go. All right, so again, starting out with zero chemistry, starting out with zero here because this is at time zero. So I think my pendulum is all the way on the left-hand side up here. You're thinking, no, I have not reacted hydrogen or iodine yet. And then you let the reactants react, they start to form hydrogen iodide and think your pendulum swings back and forth until you finally reach the final resting spot, right? Now then, okay, so they kind of give it away. This is 1 and this is 1 minus X. And so obviously this is minus X. So I know this has to be positive on the right-hand side. Why? Because again, you can't have a negative number of moles at equilibrium. It just doesn't make any sense, okay? So 1 minus X, that is 1 minus X. All right, so the change is negative X. And over here, then, this is a 1-to-1 ratio like this. So if I had negative 1 over here, it's going to be negative X over here, and it's be negative X over here. And this then leaves it to be 3 minus X for the equilibrium moles. So just keep in mind the pendulum swinging left and right, and you finally just got to get your final resting spot, right? Now, on this one, right, this is 1 to 2. And so I'm thinking negative X, it could be positive on this side, well, positive 2X. And so this would be 2X, right, at equilibrium, okay? So yes, the equilibrium moles are not the same as the initial number of moles. Well, of course not, because the reaction has occurred, okay? And you're thinking, it's finally come to a balance. You know, like last time we talked about like a seesaw, right? And so this one down here, let's take a look. All right. This is 1, this is 1 minus 2X. So the change here has to be minus 2X. Now, by the way, did you notice up here, do you notice up here, chemists, that it's not always is 0. It's a 0 for the products. Doesn't always have to be 0. And so the reason why chemists put this one is because, again, you know, the exam board is going to try to put something tricky in there to try to get you, you know, confused. You're thinking, oh, you're always used to seeing it be 0. Like up here, it's always 0. The other two I did is always 0. So the products are times 0 at the initial number of moles, right? However, it doesn't always have to be. In this case, it was 1. Well, that's fine. Now then, you're thinking, all right, so 1 minus 2X, obviously this is negative 2X over here. And so this is a 2-to-1 ratio like so. And so I am thinking this has to be half of that. So what, minus X? This is 2 minus X like this. And then on this side, this is going to be positive. Why? Because if it's negative on one side, it could be positive on the other, right? You're thinking the pendulum chemistry going back and forth all the time. So you can't have negative on the reactant side and negative on the product side. You can't have positive on the reactant and positive on the product. It's got to be negative on one side and positive on the other, right? So let's say, ding, 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 this is going to be positive 2X like so, right? Because 1 to 2 ratio like this. What does daisy chain these together? This is 1 to 2. And so it's a positive 2X. And so this is 1 plus 2X, right? Okay, so point the first exercise chemist was can you calculate moles at equilibrium if you know what the change is, or you don't know what the change is? And the point of the exercise is you use these ice tables like so. Ice tables, you see these on the exam as ice tables like this. And the trick is that you just add going down. That's what you do. All right, initial change equilibrium. And so you get the equilibrium number of moles like this, right? Good. All right, now, something else that they're going to ask you to do then, chemists, and so they'll say, you know, what's equilibrium moles of the reactants products? That's easy to do, but on every exam, guarantee this one, okay, is they will ask you to calculate the units. Now, the units, chemists, you're thinking, they depend on the system. And so there isn't a standard set of units, okay? The first thing we've got to do then is, first thing over here in my little scratch area here, right, we need to write down the expression for Kc. Now, we'll admit, chemists, in year 13, when we do rate laws, okay, I do loop back into this one and I explain to you where the expression comes from, right? This is your mass action expression, where it comes from. But because we haven't got to rate laws yet, I thought, well, we'll just keep it really close in the module, and it's just the concentration of the products raised up to the power over the concentration of the reactants raised up to the power, okay? And like I said, on the module on rate laws, we get into this and I show you where the rate law comes from and how the rate constants cancel out, and you're actually left with this. You can actually derive it, okay? But for right now, we don't need to worry about that. So anyway, Kc. Well, I'm going to call it Kc. Why? Because I am dealing with a concentration. And so this then is the equilibrium constant in terms of concentration. That's what it is. All right. Not a big deal in year 13. We do equilibrium constants in terms of pressure, and so that's known as Kp. We also do them in the module on acid and bases, and so Ka is the equilibrium constant for an acid, and if you're following along, you're going to say, well, hey, I bet the Kb is the equilibrium constant, the equilibrium constant for a base, and you would be correct. All right, so here we are. Very first thing then is I got to write down Kc expression. Oh, before I forget, I've got to put down at a given temperature, meaning the equilibrium constant right there is only valid at this temperature. If you change the temperature, you change the equilibrium constant, you have to rework everything again. So Kc then is equal to, well, products, this would be PCl5 over reactants, PCl3 times Cl2, okay? And because there isn't any number in front of these species here, it's assumed to be 1 to 1 to 1. This is why you've got PCl5 over PCl3 to Cl2. Now then, you're thinking, what's the quick way of doing this on the test? All right. Well, the quick way of doing it on the test, chemist, is this. You keep in mind the concentration, square brackets, concentration, is equal to moles per decimeter cubed, right? And so I've got moles per decimeter cubed up the top. And on the bottom, I've got moles per decimeter cubed for the BCl3. And I've got moles per decimeter cubed for the CO2. Now, change pen colors here. Back using this green. All right, this decimeter cubed, this one, this, and this cancel out. And so all I'm left with is, you're thinking, actually, I can probably do that a little bit better. I do like this. Moles per decimeter cubed up here, cancel with moles per decimeter cubed up here. And so what I am left with is thinking this will be 1 over moles per decimeter cubed, wouldn't it? Because everything else is canceled out. Now, totally acceptable to leave this as is on the exam. All right, they would accept this, or if you wanted to, all right, in my Syracuse orange, I'm going to bring the moles up here and the moles up there. And you know what the rule is, if it moves past the line, the fraction bar, and it changes sign. And so this is moles per -1 because it moved over the fraction bar. And this is decimeters cubed. Right, so this is the first one. Now, you're thinking, well, yeah, is there a fast way of doing it? Well, there is. All right, I'll show you what the fast way of doing it is, but let's make sure we've got this one down first, the actual concept. And so next one then, KC, all right, again, products, and H2 cubed times CO over CH4 times H2O. Okay then, so I'm thinking green pen here, do this, right. Let me write it out first, hold on. This would be moles per decimeter cubed with H2 times moles per decimeter cubed with CO over, let's see, moles per decimeter cubed CH4 and moles per decimeter cubed for the H2O. So green pen, all right. This cancels out with that. And then I've got one of these on the bottom, and so it's going to cancel out with one of these on the top, so the cube becomes a square. And then you just need to bring in, the square. So this would be moles squared. And right, so this 2 goes over here, moles squared. And this would be bring in the 2 decimeter to the -6, like so. Right. Now, this is your second one. Okay. Next one, right there then. So let me do the next one, and then I'll show you the quick way of doing it, okay? I put this one in because it's kind of odd. Well, it's one of the systems we always use, isn't it? And it's like, yes, you know, like all of these, the last two were just systems that we used previously, always on the exam board. And so this would be what, HI squared up the top over H2 times I2 on the bottom. And so this is going to be what, moles per decimeter cubed up the top squared. And at the bottom, this is going to be, well, moles per decimeter cubed. I think you can see where I'm going with this one. Times moles per decimeter cubed. All right, so 1 mole per decimeter cubed for hydrogen, 1 mole per decimeter cubed for the iodine, this is going to be squared. And so if I change pen color to green, then you find out that the moles per decimeter cubed squared this cancels out with that. And you go, well, that's odd. Well, what do I write down? Well, you write down it's unitless. So yes, unitless. Okay. It's supposed to be unitless. Don't depend on unitless. Right, unitless. That's the best it's going to be. Right. Now, so chemists, the units of Kc are always going to be on the exam, and they're always going to be worth a point, and so it's worthwhile working this one out. The units of Kc are not fixed, meaning they depend on the system that you're working with, and you've just got to sit down and do a little bit of algebra and work it out. Now, is that okay, Graham? We've got moles per decimeter cubed is your standard change, your unit of concentration there. So I see that it's, you just put in the moles per decimeter cubed and start counting things out. What's the fast way of doing it? Well, the fast way of doing it is this one. Is what I'm going to say is I'll do it in neon pink. Right, if I was doing this one on the exam, because you're thinking, it's just got to be the correct answer. They don't care how you got it. It's got to be the correct answer. Right, the units of PCl5 cancel out the units of CO2. And so therefore I'm left with, immediately I know that I'm left with 1 over moles per decimeter cubed. In other words, I can save some time and I don't need to start counting things out, writing it out, then counting it out. No, you just cancel out this. Now, same one with this one on the bottom. This is going to cancel out with that, and one of these cancels out with one of these and says square. And so this is where I got the moles per mole squared decimeter minus 6 from. All right. So this is the fast way of doing it. Because again, on the exam, they don't care what mathematical step you took to get the unit. All they want to know is what is the unit is worth a point. So this is this one. Now, so far, we're doing good. Let's then have a look at some actual problems. All right, so here we are then. So I'll pull these. All right, let's take a look then. So all right, you've got 2 moles of PCl5 vapor heated, temperature T. They've got to tell you it's constant temperature. Because chemists, that Kc is only for a given temperature. The only thing that can change the value of Kc is a change in temperature, because it's constant. Right, oh yeah, it's constant. Right. In a vessel of volume 2 times 10 to the 1 decimeter cubed, the equilibrium mixture contains 1.20 moles of chlorine. All right, calculate Kc, this equilibrium at this temperature. Okay, so first thing I'm going to do then, chemist, is change out of neon pink. Let's get back into blue, and we're going to do ice table here, ice, initial change, equilibrium. All right. Change equilibrium. So you get working out points. Now, you're thinking, ding, 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 2 moles of PCl5, so 2 moles of PCl5. They told me the volume is, side note, volume is, can I just call this 20? I mean, I know it's 2.0 times 10 to the 1, but I just call it 20 decimeters cubed. All right, the equilibrium mixture contains 1.20 moles of chlorine, and they want to know what the value of Kc is. All right then, so quite legitimate to say the initial value of PCl3 and CO2 is 0. True. Why? Because nothing has happened yet. We call the pendulum is all the way on the left-hand side on the reactants, and then I let it go. It's going to swing back and forth until you reach this final resting spot. So this is 0. Okay. The change has to be plus 1.2. We'll do this plus 1.2. because you know you add going down. You add going down like so. So 0, 1.2, this is a 1-to-1 ratio. So this has to be positive 1.2, which means that this is positive 1.2. Right, it's going to be positive on this side, on the right-hand side in this example, because otherwise you would have a negative number of moles, which doesn't make any sense. So on the left-hand side then, the daisy chains together, 1-to-1. Left-hand side has to be negative 1.2, which, what's that, 0.8? Like so, right, 0.8, like this, right. Now, this is moles. What they want to know is a value for Kc. Well, Kc, if you recall, all right, Kc is in, well, it uses concentration, doesn't it? So the moles, not actually helpful right now. So I've got to divide by the volume. So I'll just give them blue. I'm going to divide this by the volume, which is 20. All right, the volume, which is 20 going across. Okay. And then I'm going to get my equilibrium in my concentration, which is a bit more helpful. Okay. All right, calculators on, chemists, hold on right here. So I've got 0.8. Hold on. Do I do these live? Yeah, so 0.8 divided by 20. I got this to be 0.04. All right, 0.04. And let's see, 1.2 right there, divided by 20. Make sure my mental math is correct. This is 0.06. And this is 0.06, right? So here's my equilibrium concentration. Like this is, start out with equilibrium moles, and it's moved to equilibrium concentration. And then you're going to put it into the Kc expression. So move my video link over here. Kc is equal to, well, the concentration is Cl2 times the concentration of PCl3. You know, products raised the appropriate power, the stoichiometric coefficient, if you would, in front of the species over PCl5. And so Kc is equal to, plug the numbers in. Now, chemists, when you do these, right, you're thinking you've got to show all the working out. So I know it's 0.06 and it's 0.06. You could easily square that. But on the other hand, you know, write down for the examiner that 0.06 to 0.06 over 0.04 to get all those working out points. And then you get Kc is equal to, so hold on, 0.06. All right, hold on, divided by 0.04. I do this live, right? I got 0.09. 0.09 when I did it. Oh, so 0.06 times 0.06. Yeah, divided by 0.04 is indeed 0.09. Right. Units, well, I'll change pen colors. All right, we'll do this one using the shortcut method. The PCl3 and the PCl5 units cancel out. So put down the units. I'm not talking about PCl3 and PCl5, I'm talking about the units. The units in orange cancel out. And so I am left with just a unit at the top of concentration, which is moles per decimeter cubed. Voila, done. Now, you're thinking, yeah, but you know what? So we get this. So we got this value, right? Like Kc, we get this value. What exactly does it mean? Well, we'll get into this in a problem, but look, Kc, keeping in mind that Kc is the concentration of products raised to the appropriate power over the reactants raised to the appropriate power. So you're thinking, Well, Kc could be greater than 1. It could be equal to 1. I mean, I've taken to get somehow the concentration of products is equal to the concentration of the reactants. In a rather weird example, it could equal to 1. You know, everything could just like cancel out. Or Kc could be less than 1. Yeah, Graham, okay, where you going with this one? Well, if Kc is greater than 1, this must mean, and we'll talk about this again, but look, this must mean that the products are larger than the reactants, because in the fraction, the numerator has to be larger than the denominator to go cancel out. And so here's my little equilibrium sign is going to favor products. Ah. And I'm taking a guess, going, oh, I get it. So down here then, if it's Kc is less than 1, then the products must be smaller. The concentration of products must be smaller than the concentration of the reactants when you put everything into the equation, everything else. And so you're thinking, right, so therefore the equilibrium position, my little symbol there, must favor reactants. And so then this one here, well, if it's just equal to 1, well, then the equilibrium position just kind of like, it's in a weird position. It favors neither side. Kind of an odd one to have, but mathematically it could work out, right? All right then, so you're thinking if it's 0.09, all right, if it's 0.09, this means that the equilibrium position is less than 1. And so I'm going to put down, although they didn't ask us, we'll put down this favors the reactants. It's less than 1, right? All right. Now then, how about this one? No, was that a dupe of 13? I believe it was. Okay, all right, so don't have to worry about this one then. All right then, so in the following equilibrium, Kc is 54.1. Okay, hold on. So you're thinking 54.1, is that larger than 1? Yes, it is. And so I'm going to annotate this and say my equilibrium position then favors products. Has to be. Why? Because, I'll move my video link. Because Kc is larger than 1. So the products, the equilibrium position must be favoring the products, because otherwise Kc would not be larger than 1. The products on the top, the numerator, must be larger than the reactants, the denominator on the bottom. Okay. And so the equilibrium mixture is found to contain H2 to a concentration of 4.8 times 10 to the minus 4, and Hi to a concentration of 3.5 times 10 to the minus 3 moles per decimeter cubed. What's the equilibrium concentration of H2? All right then, so chemists, on this one, all right, let me do this one where if I teach you one thing, then you also learn something else, like I know one of these embedded teaching things. So look, start off in blue, go back to blue, right, in blue, right. Kc, right, done the expression first, Kc is equal to, well, Hi squared, yes, over H2 times I2. Right, so Hi squared over H2 times I2. Right, now, they're looking for I2. So how I would do it, chemist, is I would rearrange this and I get I2 on the left-hand side. So I would say I2 is equal to Hi squared over Kc times H2. Right, now chemist, how you do math may be totally different to the way that I do math, okay, because my math is old, but all right, if I do it over here, sidebar, maybe you do the rearrangement thing. over H2 times I2. So maybe you multiplied both sides by I2, multiply both sides by I2. So the I2s cancel out. And then, so you got what, I2 times KC is equal to HI squared over H2. And maybe you divide it through both sides by KC. Right. All right. So I'm thinking I2 is equal to same thing as I got, right? HI squared over KC times H2. Right. Now, let's plug everything in, the values in. So if I plug the values in, right, I2 is going to be, well, HI squared, which they told us was, hold on, ding, 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 H2. HI was what 3.53 times 10 to the minus 3. And let's see, H2 was 4.8 times 10 to the minus 4. And let's say KC was 54.1. So we put this into the calculator and let's get the first bit done. So I2 then is equal to, here we go. We had 3.53 to the negative 3. All right, and then we're going to divide this by 4.80 to the negative 4. All right, and then you go divide this by 54.1. And right, so hold on, I got 0.13, so hold on a second. Right, hold on. Let me just make sure I got this one completely correct here. Good. Yes, so hold on here, H2. So actually, all right, if I check it again, I got 4.8, just did the rework, 4.80 times 10 to the minus 4, right? Now, you're thinking, well, hold on a minute. Could I have just said, could I have just said, and for the mathematical people out there, you could have done this, right? You could have said, well, you know, H2 and I2, could I have said that it's a 1-to-1 ratio? And so therefore, if H2 was 4.8 times 10 to the minus 4, and then I2 would also be 4.8 times 10 to the minus 4. Well, the problem with doing it that way is it just so happened to work out that you could do it with this example. It just worked out that you could do, say, like a 1-to-1 ratio. Yeah, they do actually balance out. But this is a technique you need to learn. So when you do this calculation on the exam and in the other problems, you know how to solve the variable, all right? So on that one, I would be a little bit careful and I wouldn't automatically say that it's a 1-to-1 correspondence, because you know that the concentration at equilibrium of the reactants and products does not have to, they're constant. They're not equal, not the same. In this instance, it worked out because it was a mathematical fluke that it did. But go be careful about that one. You got to think, no, the better way of doing it is just the one where you solve the variable I2, the concentration I2, and then it's always going to work. You'll always know how to solve for one of the concentrations, okay? So anyway, this one. Just wanted to point out that, yeah, it did work out to be the same value, but it's not always going to be, right? Now, meanwhile, the reason why I put this one in is because my wonderful chemist is this one here. B. Ooh. Little bit tricky. All right, so B. So let me first off copy over back in blue, copy over the value. Or the expression we've got here, Kc is equal to Hi squared over H2 times I2, right? And the reason why I put this one in chemistry is because they are trying to trick you on this one. So they said you double the concentration of hydrogen, what effect would it have on the equilibrium position and Kc? All right, so on this one, first one is a Le Chatelier's principle. All right, so I'm going to increase the concentration of H2. We said away from the side you add. And so I'm going to say if I increase the concentration of H2, then my equilibrium position, all right, is going to move over to the right-hand side. It's going to favor products. Okay, so hold on and right. This one's in the equilibrium position. It's going to favor the products, and this is nothing more than Le Chatelier's principle, right? Right, and we did this in the previous lesson. Right, now the next bit is a trick question. It said, what effect would doubling the concentration of hydrogen have on the Kc value? Answer, no effect. Ooh, tricky, right? Why? Why? Because the Kc is a constant at a given temperature. Right? So if you increase the value of H2, what's going to happen is, if I draw it like this, if you increase the value of H2, then yes, your value of H2, the concentration of H2 increases, agreed. All right, and you're thinking, so does the value of Hi, because you produce more product, okay? So you're thinking, yeah, and of course I2, well, we're not really going to get into I2, all right? So I2 is like, leave I2 alone for right now. But point being is that yes, if you increase the value of H2, the reactants, H2 times I2 are the reactants. If you increase the value of H2, then yes, you're going to shift the equilibrium position over to the right-hand side, and you're going to increase the concentration of Hi proportional to the change in H2. And so everything readjusts and the value of Kc remains the same. So it's like if you make the denominator slightly larger on the fraction, well, then the numerator on the fraction also has to increase as well, because the system, the pendulum, readjusts, and you're thinking the value of Kc remains the same, okay? So please understand the difference between equilibrium position, which can change, Le Chatelier's principle, right? Equilibrium position, that can move left and right reactants products, and the difference between the equilibrium constant. They're not the same. And this is the type of question that I think the exam board will put down. Did my equilibrium constant, all right? Okay, next one. What effect would increase the temperature have on the equilibrium position and Kc? Oh, by the way, they got delta H is greater than 0, and so that would make it endothermic, right? And so, all right, because they said delta H was greater than 0, so it's endothermic. So yeah, you're thinking I'm going to put my enthalpy on the right-hand side. Now then, if I increase the temperature away from the side you add, isn't it? So down here, if I increase the temperature, it's like I am adding energy in. My enthalpy is going to move over to the right-hand side. True. So let's say my equilibrium position moves over to the product side, yes, away from the enthalpy, which is on the reactant side. And then didn't I say that the only thing that can change the value of Kc is temperature? Well, now you got to stop and think, well, does it go up? Does it go down? All right, there's nothing to memorize here, chemist, nothing at all. What you got is this, you're thinking, right, if I increase the temperature, I shift the equilibrium position over to the right. And so therefore, I'm going to produce more products. And I'm going to have less reactants. And so obviously the numerator is now going to be larger than the denominator, and so the value of Kc increases if you increase the temperature for an endothermic reaction. Now, on this one, chemist, I would not memorize it, because on the exam, oh, you know, maybe get it backwards, I don't know. But if you draw it out like this, if you map it out like this, you say, yeah, it makes sense because I produce more products. And therefore, my numerator is larger than my denominator, and the value of Kc just goes up. Right. So the converse would be then if you decrease the temperature, what's going to happen? You decrease the temperature, the equilibrium position, all right, is going to favor the reactants. Everything slides over to the left-hand side. And then you're thinking, now you've made more reactants and you've got less products. So therefore, the value of Kc decreases for an endothermic reaction. Now, what you need to do, chemists, is you do need to do plenty of practice problems on these, and you're thinking, yeah, this is one that they're going to ask you. You know that they're going to ask you something about the temperature because you can have endothermic and exothermic, you know, systems. Then they can say, do you increase or you decrease the temperature? So all of a sudden you have like multiple options that they can ask you about the same concept, all right? But this was this one. Right then, so let's see. All right, so the increase of temperature, you shift it over to the right, this endothermic, and you would increase the value of Kc, right? All right then. So let's see, hold on. Coming down to this one, right? Here we go, then comes on this one. Let's say Kc of the equilibrium below. Oh, it's the production of nitrogen oxide. Is 0.03. So Kc, write this down, is 0.00360 at temperature T. Yeah, they got to say it's at temperature T, yes. And 1 mole of N2, so better do the ice table straight off the bat. But you know, this chemistry, I'm always doing the same thing, right? So 1 mole of N2, 1 mole, and 1 mole of O2 are allowed to reach equilibrium. What mass of NO will be present in the mixture? Well, first off, I write down this is 0, right? Because nothing has happened. And you're thinking, oh, hold on a minute, but they haven't given us anything else. What was mean? Right, so hold on. Better do what? Minus x and minus x. because it's got to be losing on the left-hand side, because there's nothing on the right-hand side. We're called pendulums, we can left and right. And so this is obviously a 1-to-2 ratio, and this is 1-to-1. So are we thinking this would have to be positive 2x? Right, so add going down. So you've got 1 minus x and 1 minus x like this, and this would be 2x. Okay. I write down my mass action expression, my KC. Always put everything down in chemistry. You make sure that you've got all the points coming in, working out points at NO squared over N2 times O2. And again, I was going to write down 2x squared. I'm just going to write out to make sure the examiner knows I know exactly what I'm doing. 1 minus x times 1 minus x. I know it was, you could just square it, but got to make sure you get all the points you can. So let's say, so here then, so KC then would be 2x, well, 2x squared. All right, so 2x squared over 1 minus x squared like this. Okay, and this is going to be what, 0.0036. Okay, now, right, what they want to, well, first off, what we need to do is we need to get the value of x, because we're looking for this. Now, chemists, I could, I guess, bring the denominator over to the right-hand side, you know, distribute the 0.0036, form a quadratic equation, or could I just take the root of both sides, like so, and so this would be, what, 2x over, all right, 1 minus x. Then you take, we take the square root of a fraction, you take the square root of the top and the bottom, right? And then, hold on, is this 0.06? I believe it's 0.06. Right, it is indeed 0.06. Now, you may have noticed, you say, yeah, but hold on a minute, hold on. This is in moles. And they didn't actually give us the volume, but this is in concentration. So how are you going from moles to concentration if they don't give you a volume? Right, simple, chemists. All right, if volume is not given, if volume is not present, all right, make it easy on yourself. Just put down V equals 1. Okay. So you're thinking, oh yeah, well, it's the same round bottom flask, all right, closed system with a stop on it. So yeah, I'm just going to do over 1. So I set my V equal to 1. And therefore, you know, as long as you write down if volume is not present, V equals 1, the examiner knows that this is V, because obviously this is concentration over volume. Therefore, you're allowed to do this, and therefore you get this. And then let's say if I solved for, ding, ding, ding. All right, so let's say if I got 0.006 on my calculator, got that. And so I'm going to bring this over here now. I'm going to bring this entire thing over there. So I've got what? I got 2x is equal to 0.06, all right, times 1 minus x like this. And so what, 2x is equal to 0.06 minus 0.06 x. Solve this for x, and I've got, I got x is equal to 0.0291. Right. X, though, was the moles, isn't it? It's not the mass. They're looking for the mass, but X was to do with the moles. So he's thinking, so X is 0.0291. Well, then the moles of NO was equal to 2x, which is, double this on the calculator, I got 0.0583, hold on, 0583, like so, boom, moles. And then you need to get the molar mass. We move my video link. Got to get the molar mass, don't you? So the molar mass of NO is equal to what, 30? All right, grams per mole. Yeah, only in A-level chemistry would NO equal 30 make sense. Right, and so therefore you're thinking the mass of NO is going to be 0.0583, all right, times 30, which is coming back as 1.75 grams. Okay, so on this one, chemists, as always, set the ice table up. All right, the initial, that to give you slick on the initial of the product wasn't stated, so assume it's 0. Didn't give you anything to do with the change, so use the variable x, link it into the ratios in the balanced chemical equation at the top there. Because volume was not present, just set b equal to 1, all right? And then write down your expression of a Kc, solved it, all right, for x, got the moles of NO, and then converted it over to grams. So this one, all right. So hopefully then, chemists, we are making a bit of sense here. All right, so hold on, this one here. Okay, ding, ding, ding. Hold on. Right, so, okay, this is going to be, probably like the toughest one we can do. All right, so you got to solve a quadratic equation. Now, chemists, you need to check with your exam board and make sure if you need to solve a quadratic equation. All right, for this module on equilibrium. All right, then, so anyway, all right, so let's say the Kc value was 10, so write down some notes here. The Kc value was 10. All right, at temperature T, yes, okay, because we know the only thing that can change, the value of Kc is temperature. And so I better put down my ice table like so. 1 mole of the ester. All right, now chemists, we probably haven't done esters yet, but this is an ester right here. And so, okay, bear with, this is an ester, right? And you'll do esters in year 13, okay, but this is your ester. So 1 mole of this, and you got 5 moles of water like so. And the mixture allowed to reach equilibrium, okay, dynamic equilibrium, yes. How many moles of each species will be present at equilibrium? Well, they haven't said anything about what's on the right-hand side, the acid or the alcohol on the right-hand side. We do this in year 13. This is the hydrolysis of an ester back to the acid and the alcohol, but never mind. Put down a 0, 1 is 0 here like this. Because they haven't done anything, I'm going to write down this is minus x, and this is going to be minus x because it's a 1-to-1 ratio, right? 1-to-1, and then it's just like daisy chains across, doesn't it? 1-to-1 and 1-to-1. All right, then, so negative x on the left. It's got to be positive x on the right. Why? Because otherwise you'd have a negative value of moles at equilibrium that doesn't make any sense at all. And so at equilibrium, I got what, 1 minus x, and I got 5 minus x, because you add going down x and x. So better note on here, you add going down, right? And so this is in moles. Now, did they didn't give us a volume, so I'm going to put down let volume V equals 1, because they didn't say what it was. All right then, and so divide everything through by 1. And so now I got my equilibrium in concentration. All right, well, this, just because it's 1, it's going to be 1 minus x and 5 minus x and x and x. Okay. I've got to write down my expression for Kc. So Kc is going to be, well, products. Here's my acid. Here's my alcohol. And here's my ester. And here's my water, right? Like so. Okay, now look at my notes real quick. What I better do then is I better put down well, an extra step, x times x, all right, for the reactant and the products, and 1 minus x and 5 minus x for the reactants there, right? And the reason I can do this is because I let volume equals to 1, all right then. And so this is going to equal to 10, all right? So what we're going to do now then is I need to put this into a quadratic equation, don't I? Because you're thinking this is equal to, you know, x squared over 1 minus, whoops, minus x and 5 minus x, right? Okay, so new page, put this into a quadratic equation. So chemists, if your exam board requires you to do this one, well then by all means you need to crunch through these because these are going to be like the most difficult ones you could possibly do with quadratic equations. If you check your spec and you find out like things like AQA, they don't require the quadratic to be used anymore, well then, hey, good one, you know, you think you don't have to worry about it. So anyway, here we are then. So what I'm going to do then is on this side, I'm going to bring this and this over to this side here, okay? So I am thinking that if I do that, I got 10, yes, and then I've got 1 minus x, and I've got 5 minus x. Brought that over is equal to x squared, and I need to distribute this, don't I? So I've got 10 times, let's do this. But 5 times 1, I've got what? 5 right there. All right, hold on. 5 times 1 is 5, and 5 times minus 5x, like this. Yes, so I got on. 1 times 5 is 5. I'll try doing the other way, easier. 1 times 5 is 5, and 1 times x is minus x, and I got minus x times 5 is minus 5x, and then I've got x times negative x is plus x squared, and this is going to be equal to x squared. Then bring this in. All right, so 10 times 5 is 50. All right, just read off my notes now. 10 times 5 is 50. Let's say, oh, this, by the way, let me do this. Let me clean this a little bit. 10. So this is going to be 5 minus what? 6x plus x squared. All right. Is equal to x squared. And so this is going to be what? 50. 50. Bring this in. 10 times 5 is 50. Minus 60x. All right, bring this in. All right, plus 10x squared, like so, is equal to x squared. And then, all right, I now need to bring this over here. So I can bring this over here because I need this to be 0. And so I got what, 50 minus 60x. All right. Plus 9x squared is equal to 0. All right, now then, okay, I just need to rewrite this. And so wouldn't this be 9x squared minus 60x plus 50 equals 0? All right. Now, you need to then use the quadratic formula. Most of your calculators these days do the quadratic, but well, that's like, you think, right, and so x is equal to what? Negative b plus or minus the square root of b squared minus 4ac all over 2a. Like so, and so obviously this is a, this is b, and this is c. Okay, so if I put everything in then, all right, I'm going to get a lot of like sidebars here, isn't it? Like this, like that thing. I'm going to get x is equal to what? Ding, 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 60. All right, so hold on. Oh, b is negative 60, so negative b is 60. All right, plus or minus the square root. Can move my video link. Hold on. The square root of b squared, what's that? 3600. All right, minus 1800, because it's negative b. So b, if b is negative 60, then negative b is 60 plus or minus b squared. That's obviously negative 60 squared, yeah, minus 4 times 9 times 50, like so, all over 2a, so 2 times 9, like so. Anyway, we plug it in, and you get x is equal to 60 plus or minus the square root of what, 3600 minus 1800 all over 2a, which is what, 18, 2 times 9 is 18. Right, so if you solve it, you get two roots, don't you? You get x is either 0.976 or x is equal to 5.69. And you go, well, that's just great. I've got two of these. Now, which one could it possibly be? Well, come back to the actual expression, chemists, right here. Look at this one. It's 1 minus x. And so you can't have negative values of your moles. And so x has to be less than 1, doesn't it? Because if x was 5.69, this would be negative, what, 4.69. That doesn't make any sense, a negative number of moles. And so over here, if I get my board to come down like this, but this one gives a positive number of moles. At equilibrium. So this is how you decide. Yeah, they are both mathematically correct, but 5.69 is, well, it's too large. You would have negative values of moles at equilibrium. That doesn't make any sense. So anyway, if we then come over here, then this is going to be what, 1 minus x, 5 minus x, x, and x. Right then, so I tell you what, in orange, Syracuse orange, yeah, here we go here. And so x then, like this is, oh, it's easy, this is just 0.976. And this is 0.976, like this was easy. All right, so this is going to be 5 minus 0.976. And so this is going to be 4.024. Final answer, and obviously this is 0.976, and so the ester is going to be 0.024, like so. Right then, Oh, okay, very well. Got it. Right. So this is the most difficult one using the quadratic. Please check with the exam board, make sure you do actually have to do the problem. All right. Most of it will be done on the calculator. That's the button, you can press it. Or if not, just use the quadratic formula right there. Okay. And here we are. So last one. All right, here we are then, chemists. You've done well today. Awesome as always. Right, here we are on this one. Let me change pen colors like so. Back into blue. All right. I wanted to pick this one. This is the last couple of questions right here. Catalyst. It says, well, what's the meaning of the term catalyst? Well, is going to be a species, a substance that lowers the activation energy. All right. How does it work? All right. So there's a lesson I do on catalysts. All right. It provides an alternative pathway with lower activation energy. Okay, it provides an alternative pathway, lower activation energy. So one for this, right? Term catalyst species lowers activation energy. Provides alternative pathway, lower activation energy, yes. And you could also say that it weakens the bonds in the reactant, reactants. So we get into catalysts in year 13, chemists, and in that module, what I do is I teach you about the fact that catalysts tend to be D-block elements, like transition metals, and there's a reason why you always see them be like iron or platinum or palladium. And we get into adsorption and deabsorption and active sites, and the weakening of the bonds in the reactants. Okay. Now, the reason why I picked this one, then it's to state the effect, if any, of the catalyst on the time taken to reach equilibrium. And so this one, all right, is rate. And so I'm going to say, it's supposed to be closed bracket, so rate is going to increase the rate of reaction. And so therefore, you know that rate is inversely proportional to 1 over T. And so therefore, it's going to lower the time taken to get to equilibrium. All right, voila. Now, the next bit then is, the tricky one. What's going to the effect of the catalyst position of equilibrium? Of a little symbol like this. Answer, none. So this is the tricky one. Why? Well, because the catalyst lowers the activation energy for the forward reaction, and it lowers the activation energy for the reverse reaction, meaning there's no overall change. So the rate forward and the rate backwards have been affected equally. Therefore, there's no change on the position of the equilibrium. However, you do get there faster. Okay? Anyway, chemists, this was this one. This was all about the calculations for equilibrium. So I hope you enjoyed that one. And I will see you next time. All right, so have a good day, and I'll see you next time.